In this video, I'm going to show you step by step how to design the schematic and PCB layout for a battery charger circuit. This battery charger is specifically for charging lithium-ion or lithium polymer batteries, which are by far the most common types of rechargeable batteries used today in most products. We'll be using the BQ24092 battery charger chip from Texas Instruments, which is a 1 amp single cell lithium ion charger. Hi, I'm John Teal. I'm a former microchip designer for Texas Instruments and an entrepreneur who developed and brought my own product to market. Now I help entrepreneurs, startups, makers, inventors, and small companies develop and sell innovative new electronic products. Okay, let's get started. The circuit that we're going to be working on in this video is actually part of a much larger design that's for an entire microcontroller. We're just going to be looking at the battery charger portion of that design. And specifically what we have is a USB or a micro USB connector that we're using to supply the battery charger. So you just plug in a USB charger, and then that has a 5-volt output, and that's what we're using to feed into the battery charger. The 5 volts comes off of from the micro USB, and now it goes over to the battery charger. And the battery charger comes in to the input pin of the battery charger. There's a 1 microfarad decoupling capacitor. In almost all cases, you're going to want a decoupling capacitor on the chip, on each chip. And typically this is something you should look at the data sheet for recommendations on what they recommend. I'm actually going to do that. Also, I want to look at each circuit in the data sheet so you can see how I drew this. Let's start. We'll look at, this is the BQ24092 battery charger. I'm going to just pull that up here. And you can see it's a single input, single cell lithium ion, lithium polymer battery charger. The single cell means 3.6 volts, one cell. If you stack those up, if you put 2 of them in series, then you get 7.2 volts. And this charger can't do that. This is just a single cell charger, which is most applications are going to use a single cell, but it can charge with up to 1 amp of current. Let's scroll down here, and typically when drawing the schematic, there's a lot of information in the data sheet, obviously, but the 2 areas you're going to want to start with are like a typical application circuit, where a lot of times, especially for TI data sheets, they'll include a typical application diagram on the front page, which is the case here. But in other data sheets, you'll have to go into the index here, table of contents, and you can see here's a typical application. It's just the same one that they have on the front page, but just keep in mind a lot of data sheets don't have this on the front sheet, which I happen to like, but just keep in mind a lot of them don't have it. This is pretty much the exact same circuit that I have. We have the adapter or whatever you're using to supply the incoming voltage goes to the input pin. Then we have the I set pin, and this is what has a resistor here, and they give formulas for calculating the value of this resistor, but this sets the charge current. So how much current can go into the battery to charge it. Obviously, the higher that is, up to 1 amp is what this charger supports, the faster you can charge the battery. But it depends on the battery size. For instance, if you had a 500 milliamp hour battery, then you most likely would only want to charge that with 500 milliamps, which is considered like a 1C charge rate. For this one, this can go up to 1,000 milliamps, so you could charge a 1,000 milliamp hour battery. You can still use it to charge a much bigger battery. It could be a 3,000 milliamp hour battery, but just the charge rate's going to be slower than if you use the maximum charge. So just in most cases, there are batteries that can charge and discharge at much higher rates than 1C, but typically just use that as the starting point. If you have a 2,000 milliamp hour battery, then ideally you'll want to charge it with up to 2,000 milliamps, which would be the maximum it can tolerate, and that speeds up the charge time. All of this can be set with this resistor, and you'll find the formula in the data sheet for calculating that. Then VSS is just ground, basically, just another term for ground. Then pin 4 is the preterm pin, and what this does is this sets what's called a PreCharge current and a termination charge current. I'm going to discuss those in much more detail here shortly, but there are different modes of operation or different regions of operation for a lithium battery charger. And so there's the PreCharge, then this resistor here actually sets with what's called the fast charge current. I had just referred to it as the charge current previously, but it's really also, you'll see it in the data sheet, called the fast charge current. This resistor allows you to then set the PreCharge and termination currents, which I'll talk about here in a moment. And it's also set with just another resistor that they give equations for. PG is just power good. So this is an output that indicates when the power is good on the output. And the bar over it just means it's a negative polarity. So when it's low, that means the power, if the PG bar pin is low, then that means power is good. And when it's high, it means the power is not good. You can do several things with this. They have this tied to a resistor and an LED that goes to the output. Whenever the power is good, the PG pin goes low, allows current to flow through that LED and turns on the LED. You can also get rid of the LED, just have the pull-up resistor here, and then you would just tap off the PG pin, and then that could go into a microcontroller GPIO pin just to let you know the status of the charger. Then there's an iSet2 pin, and what that does is allows you to override the fast charge current set by this pin, and depending if it's high, low, or floating, you can set the maximum fast charge current to either 100 milliamps or 500 milliamps. This is commonly used for USB or older USB that has a limit of 500 milliamps. Then we have a charge, which also has a bar. This is another output pin that just tells you when the battery is actively being charged. If the battery is actively being charged, this pin goes low. Once again, they have an LED, so that turns on the LED. But this could also just have the pull-up resistor and go to a GPIO pin directly on the microcontroller. Then there's a TS pin, which is for monitoring the temperature of the battery or battery pack. And that's optional. It's typically something you want to do, but in this example, I'm gonna not use the TS pin. And then the output is the output that goes to the battery, and then you can also tap off of your system load off of this, which is what I'm doing. And everything will still work as long as the system load can't ever exceed the adapter current. If this has 1,000 milliamps maximum that it can supply, and you're pulling 1,000 milliamps on the system, then that leaves none left for the battery charger to charge the battery. Or if your 1,000 milliamps input limit and your system's pulling 500 milliamps, then that will leave 500 milliamps to charge the battery, which slows it down by about half compared to if you had the full amp. That's an overview of the schematic. We'll jump back to my schematic. You can see it's pretty much the same. I've got two resistors, one for iSet, one for the preterm, and I'm not using the PG pin just to keep it simple. I'm not using the charge output. I'm also not using the thermal sensor. I just have that tied to ground through a resistor, which is as specified in the data sheet if you're not using that pin. iSet2 I'm also not using. I just have that grounded. So that means since I'm not using iSet2, that the fast charge current will always be set by R3. And then this also has an output capacitor, 4.7 microfarads. That's the circuit. Now let's go back to the data sheet for the charger. And this time I want to look at this chart. You'll see this chart is repeated in lots of various data sheets, but it shows you that the way that a lithium battery is charged. And there's a lot of detail here I'm not going to necessarily go into, but I wanted to give you a quick run through. You have the preconditioning phase. And what this is if the battery's totally dead, with a lithium battery, you don't want to just instantly start fast charging it and dumping an amp of current into, or whatever its maximum charge current is. Instead, what this does, the preconditioning phase, or you'll call it a PreCharge or trickle charger. It basically just trickles a little bit of current into the battery to get it charged up enough that it can then be fast charged. And what this is doing, this is monitoring the voltage on that battery. This is what this VO with the LOV or low V in parentheses. Once the battery voltage through the trickle charge charges up and hits that threshold, then at that threshold, now it switches into the fast charge phase. And these two regions here can be looked at as our sort of fast charge. This first region is called a thermal regulation phase, and I haven't mentioned that yet, but that not all regulators are going to hit this thermal regulation phase. A lot of them will just go right into the current regulation phase. The thermal regulation phase is basically when the power required to charge the battery is so high that the battery charger, the chip itself, is heating up and hitting a temperature limit, typically almost always around 125 degrees C or higher, up to 150 degrees C. It's hitting that limit, and whenever it hits that limit, then that shuts down the charger briefly. That allows, and by briefly, I'm very minimal amount of time, just seconds or fractions of a second. That allows it to cool down, and then it reinitiates the charging. During this thermal regulation, it's sort of cycling the charging on and off just to make sure that the the chip doesn't get too hot. And this always happens at the beginning stage because this uses a linear regulator or a linear charger. If you have a really big difference between the input voltage and the output voltage, then that's going to cause it to dissipate a lot of power. When you're first charging up, say, a dead battery, when you're first starting the fast charge, that's when the battery voltage is at the lowest. That means your output voltage is at the lowest. And then because that's at the lowest, that means your differential from input to output is at the highest. This just happens to be the most power dissipation happens. But once you get the battery voltage up to a certain point, then the linear charger won't be dissipating so much power, and then it would just charge at the fast charge current, which can be up to 1 amp. Then once you finish the fast charge phase, then it goes into a voltage regulation or charge termination phase. And what this does is now this supplies everything up until here has been just regulating current that goes into the battery, not the voltage. In this case, we're just supplying a 4.2 volt DC supply to the battery, and you're monitoring the current. And when the current gets to a certain point, which is the termination level, charge termination current, then that's when the charge process shuts down, and that's what's happening here. This threshold, that the charge current termination threshold, as well as the preconditioning current, how much current used during this pre-charge or trickle charge stage, are set by that preterm resistor. And it's set up, obviously you're setting two values with one resistor. The way they do that is essentially the pre-charge current is twice whatever you set the termination current at. Let's just say you set this current termination at 100 milliamps. Then that means it would do a trickle charge of 200 milliamps. Okay, so that's a run through on the lithium battery or charger and the different phases of a charger. And this is why you should never try to do this manually with your own circuit. There's a lot of complexity in this. There's a lot of work that goes into designing a lithium charger. So be sure to use a chip for this that has all these functions integrated already. Now we're going to do the PCB layout for the battery charger, which is the BQ24092 from Texas Instruments. For a battery charger, and as I've mentioned, and we'll get into it in a moment, the boost regulator, you definitely want to look at the data sheet for their layout recommendations. It can also be the case for the linear regulator, but those are typically a lot less complex to lay out. We're working on the battery charger here. Let me go ahead and zoom in on the battery charger sub-circuit. That's this here, and then This is U4 is this device here. I'm going to just kind of pull this down here. I'll go ahead and rotate it. Pin 1 is in the top left corner. And for this type of chip, you can see this is indicating this little circular notch is what tells you what pin 1 is. It just shows you this is the end with pin 1, and it's almost always on the left side. That's going to be pin 1. You could add a dot if you wanted, but this is also a standard way of signifying what is pin 1. Let's start by, let's look at the data sheet for the BQ24092. Okay, and here was the typical application circuit, which is pretty much what we're doing. Let's go down to the table of contents. There's a layout section, layout guidelines, and a layout example. Let's just go here. And you can see they give you an example layout. There's a lot here. This is kind of a convoluted example a bit because they're not just focusing purely on this chip here. They're kind of showing some other stuff that's also part of the design. But up here, they kind of specify the main criteria. And this isn't going to be as critical as it is for the switching, the boost regulator. That tends to be the most complex as far as PCB layout. They basically are just giving you some guidelines. Their first guideline is the same one I've mentioned over and over, and that's to place the decoupling capacitors as close as possible to the actual pin of the device that it's protecting. So that's this first one. And then they're also saying to isolate your low current ground connections from the high current ground connections. And the reason being is, like a ground connection or any connection on a board, you look at it as a short circuit. It's obviously, that's what it's intended, but nothing is ever is ideal. There's always some resistance with that trace. What happens is if you don't separate the low power from the high power grounds, is that you'll have all this current dumping into a ground connection, and that causes an IR drop across that ground connection. IR just meaning Ohm's law, voltage is equal to current times resistance. There's an IR drop across that trace because of the high current. Well, now if you're tapping off your ground connection for some of the, say the ground connection for the chip itself or some low power sections, then you're going to have a voltage difference that's not at ground because you've got this IR drop, which is most likely is going to put it a little bit above ground. That's why you want to typically, for high current paths, you want to make sure that those grounds are separate and that they will tie directly into the ground plane. So that's what this first is saying, is to separate them. And you can even use a single point ground where you're essentially connecting the low power grounds all back to a single point. The high current path. Okay, the other thing that they're saying is the traces that carry the high currents, basically the input to the charger and the output, have to be sized so that they're wide enough to carry the amount of power. We won't be able to use minimum width traces because the BQ24092 can support a charge current up to 1 amp. We just need to make sure that we size our trace widths to be able to handle 1 amp of current. And I'll of course show you how to do that here in a moment. And then their final point is that they just mentioned that the BQ24092 has what's called a power pad. Let me zoom in here so you can see it. You'll also be able to see it in my layout, but let's just look at it here in the data sheet. This is the chip. Here are the pins. And what you can see here is this big block underneath of it. So a normal chip, there will be just nothing here, and you can even run traces under that if you wanted. But for this type, and for a lot of chips that need to dissipate power, this is basically just a big ground plane that you can see it ties into the ground, which is all this here. And you can even have vias in here that connect to ground, like a ground plane underneath on the next layer. And the purpose of this, it serves as the ground pin for the part, and a lot of parts you may also have a separate ground pin. But the main purpose of this is to dissipate power. It allows the the temperature, the heat build up in the chip to flow basically through this ground connection and be dissipated onto the ground plane that's below it. Or that's idea if you have the vias going to the ground plane below it. They don't have them in this case. The heat's going to just be distributed into this big metal plane. You can kind of look at it's a heat sink essentially. It's drawing the heat away from the component itself. That's something you'll commonly see in switching regulators, linear regulators, battery chargers, anything that can dissipate a lot of power. You'll see this power pad to help pull that heat away from the die. Those are the, I don't think there are any more. No, they kind of talk about the thermal considerations and how much power you're dissipating and how to calculate the temperature rise in that. It's not something I'm going to do in this lesson. I've done it before in some of my blog articles where I talk about linear regulators or switching regulators and how to determine how much they're going to heat up based on how much power they're dissipating. You can essentially, there's a rating for a chip and it's called theta JA, and it's what they're talking about here. The symbol here is theta, the Greek symbol theta JA. Theta, and the JA is, the J stands for junction. Think of the junction as the die itself, and A is for ambient. What this tells you is and it's going to give you this number in degrees C per watt. If this number, say they give you theta JA is 100 degrees C per watt, then that means if you put the part in a situation where it dissipates 1 watt of power, then it's going to heat, the die is going to heat up by 100 degrees Celsius. Just that's something to keep in mind. And if that were to heat up to 100 degrees Celsius, and let's say your ambient temperature, the air temperature is 25 degrees Celsius, then you add those two together. Now you've got 25 degrees C plus an additional 100 degrees C, which is 125 degrees C. And that's the highest temperature you can operate most components at that aren't military grade. Some components are only rated up to 85 degrees C, but 125 C is pretty standard. Just keep that in mind when you're designing, selecting the component and the package. A lot of this particular part only comes in one package, but a lot of components will come in multiple packages, and they'll each have different theta JAs. If power dissipation is something you're concerned with, you'll want to pick the package that has a lower theta JA. So just meaning more power dissipated, it will actually heat up less. These are all the layout considerations or guidelines that are specified in the data sheet. Now let's switch back to my layout and we can begin actually laying out the battery charger. Okay, so let's go ahead and we have U4 here, which is the battery charger chip. Now we're going to pull in all the components. I need a C15 and C16. Let's just start with those. Yeah, at least it gets a little bit easier as you get further along because there's less capacitor or less components left to choose from. So there's 15 and 16. Let's just put those there. And then we've got R3, 4, and 5. R4, R3, R5. Okay, that's all the components that we need now for these battery charger. I believe we have them all. Yep. Okay, let's zoom in here now and let's just start connecting. We've got C15 goes to U1. You can see this is the net that goes to this, and then this is the ground connection. So I'm going to rotate this, because if I didn't rotate this and I placed it, say, here, then I'm boxing myself in on some of these pins. Sorry, I hadn't updated with the right package. You can see now that this has the power pad. So what I was going to say is having this capacitor in this orientation, especially with the power pad, I boxed myself in and I can't really get these pins out very easily. If there wasn't a power pad, then I could route through underneath the dot or underneath the package, and then that would allow me to get those. If you do box yourself in, let's say that, let's just go ahead and connect up this first one. So let's say I have that, and then let's even say I'm going to connect this. This is the ground connection. I'm not going to leave this connected because I'm going to I'm going to end up connecting it using a ground plane or a copper pour. And then it will also tie into this pin here, which is the ground pin. But let's say if I was boxed in and now I need to get this pin out here. Well, how can I get it out? I could try to squeeze through there, would be one way, but the typical way is you'll use what's a via, and a via is just essentially a hole that allows you to connect from one layer to the other layer. And these are almost always you're going to use, there are different types of vias. The most common by far is just a through hole via. So it goes through every single layer. In this case, we only have two, a top and a bottom. So that's the only choice is a through hole. But if I have say a 4-layer board or even an 8-layer board or even more, let's say I want to connect a trace on layer 1 to layer 4. Well, when using through hole vias, that via also goes into layers 2 and 3. You just aren't going to connect to it, but it's there and it takes up space on those layers. So if space is extremely critical, and I mean it has to be extremely because what I'm about to suggest will typically double your PCB prototyping cost. It won't have that significant of a cost impact once you're in production volume, but for prototyping, you can use what I'm about to suggest will double the cost of the printed circuit board, and that's to use blind or buried vias. Blind and buried vias allow you to essentially connect, say you want to go from layer 1 to layer 3 without also having a via on layer 4. You can do that with blind and buried vias. They're mainly used when you need to optimize space because you don't want, even though you're connecting layer 1 to layer 3, you don't want the via taking up space on layer 4, which is what would happen with the through hole via since it just goes all the way through. And the reason it doubles the cost is because just imagine when you're stacking up the layers when they're manufacturing the PCB and they stack up the layers. Well, with the through hole, they can just stack everything up and then drill a hole right through the final stack up. But when you're wanting to only have the holes connecting through different layers, then they have to do that before all the layers are built and stacked up. It just adds extra complexity. And it's almost something it's rarely something I ever recommend that you do. The only case where I could see this is possibly if it's wearable tech and you need to squeeze every fraction of a millimeter out of the design size, then that could be a time that you would want to use a buried or blind vias. And you would also, if you're going to do a design where space is really critical, then I would not be using leaded components like this. I would be using more of the components like for the battery charger, or not the battery charger, but the accelerometer here. You can see this is a leadless package. These don't take up any extra space because these are underneath the package. Just something to keep in mind if space is really tight. It's not for this design. This is just an example, but just keep that in mind. Okay, so I'm going to go ahead and disconnect this net here. And so now, okay, so we've got C15. We've got that right next to VN. Now, the one thing I've not done yet, and I'll go ahead and do that now, is this trace width is not going to be correct. This is 6 mil trace width, which isn't going to be sufficient for carrying the 1 amp of current. You're going to have 1 amp of current flowing into this pin, and you're going to have 1 amp of current flowing out of this pin, out of the pin 10. You want to make sure that the traces going into this pin and going into this pin are all appropriately sized for that amount of current. What I'm going to do now is we're going to jump over to using a PCB trace width calculator. There are countless ones on the internet that you can find, and some PCB design software has that built in, but I'm going to just use a free one that's on the web. Let's go ahead and jump over to that now. Okay, this is the PCB trace width calculator. Like I said, there are a bunch you can choose from. This is one I happen to like, which is on Advanced Circuits, which is a US-based PCB prototype or fabrication shop. So here we go. We need a maximum current of 1 amp. So I'm going to set the input, the current to 1 amp. Then you have the thickness, and this is the thickness of your traces on the board. Obviously, the thicker the trace, it doesn't have to be as wide to carry that same amount of current. If you're using thicker traces, then you can get by with more narrow PCB trace widths. But I'm going to go ahead and select that 2 is kind of on the high end. I'm going to just knock that down to 1 ounce per square feet. This can be converted over into a thickness in mils or millimeters or microns or inches or whatever units that you want. But what you'll commonly see the thickness specified is ounces per square feet. This is how much does the copper weigh if you were to spread it out over a square foot. Obviously, if you bump over the same one single square foot, if all of a sudden you've doubled the weight, then you've doubled the thickness. But you can convert this to an actual thickness if you wanted to, but in most cases, that's not necessary. It can be when you're doing like RF feed lines and things like that. You may need to know that the trace thickness in a unit that you can is a little more usable, like in millimeters or mils. But for this, we don't need that. So I'm going to go with 1 ounce per square foot. Then we have a temperature rise. So what limits the current going through a trace is heat. If there's too much current going through it, then the trace overheats and it essentially melts, and then that just fuses it open. So this is what you want to monitor, is the heat and how much it rises. I'm just going to keep their defaults. We're just going to assume we're operating at ambient temperatures, and we're going to do a temperature rise of 10 degrees C is sort of being the limit on how much current that we can pass through that trace. You can see they give you the results for internal layers and external layers. If you have a 4-layer board, then the top and the bottom layers are external, but then you have 2 internal layers. Or if you have an 8-layer board, then you have obviously 2 external layers and 6 internal layers. And this case, for this example, we just are doing 2 layers. They're both external. But the reason they call out internal layers versus external layers different is there's airflow over the external layers. An external trace on a trace on an external layer can handle much higher current because it has airflow over it that's keeping it from heating up. But the traces that are inside are basically the temperature is essentially insulated and blocked from and doesn't receive any airflow. You can always run a lot more current through a trace on an external layer than you can on an internal layer. So because we're using external layers only, I'm gonna use that the specifications that they've given for external layers. To pass 1 amp of current, and I'm using 1 ounce per square foot of copper lay, then with a 10 degree Celsius temperature rise is permissible, operating at ambient temperature. The trace width doesn't matter. That's for calculating the resistance of that trace. In this case, we're not really concerned about the resistance of the trace, although that can come into play. You don't want a significant resistance in your power traces, because then that creates an IR drop, which wastes power and doesn't deliver the full voltage to the intended component. We're going to use this here. So I'll just use a 12 mil trace width. I'll just kind of round that up to 12 mils to do the 1 amp. And I'm always a proponent of over designing a little bit of margin of safety, as is common with all engineering. If you wanted to, you could bump this up to, say, a 15 mil thickness just to be on the safe side, especially since we're not that concerned about space. And then one last thing, just to show you, if you could bump up the temperature. I recommend keeping the defaults here, but if you wanted to push it a little bit more, let's say we bump up and we say, okay, we're going to let the trace go up 20 degrees Celsius. Well, you can see what that does is that lowered the required width to meet that requirement. So just wanted to point that out. Okay, we're going to use a 12 mil trace width minimum, and I'm going to actually probably round that up to 15 just to have a margin of safety. Okay, now that we've calculated the trace width required, I can go in and I can change the trace width of this trace here, because this will see the full 1 amp of current. And as you had just seen, we calculated that we needed 11.8 mils is the width, and I said I could use 12 or round that up to 15. But I kind of wanted to show you something. If you zoom in here, and I'm just going to measure, use the ruler, and I'm going to measure the width of these traces. And you can see here at the bottom, it's showing down here at this bottom, you can see that the width of these traces just happens to be 11.8. You could, if this was a long trace, then it would be beneficial to bump it up above what's required. But since this is such a short trace, there's really no advantage to making this any wider than the pin connection, the pad here. I'm just going to click on this, and I'm just going to go with 11.8. Shows 11.81 is the size of the, let's just do 11.8. And so that's pretty much just the same width as the pin. That's that should be good. Now where I'm bringing the power in, if I route it very far, then I'll most likely use a wider trace. Just because as the trace length gets longer, then that resistance that the trace calculator was showing you becomes more critical because of IR drops in the power line. Okay, so we finally have C15. Now the other big capacitor is C16. And you know what I'm going to do is I'm also going to rotate this around and move it up here. So it doesn't block my pins here. And then I'll just do the same with this. And I'll zoom in here, do that, but then I'm going to change that to 11.8. Okay, we've got the 2 decoupling capacitors, and now we just need all of the resistors. So we have, let's start with, we have R3 here, goes to pin 2. We're going to we'll just put this here for now. That's going to go here. Let me just go ahead and connect that up. And these can all just be back to the minimum width trace. It's only the power that requires the wider trace length. We have R3, and then we have R4. I'm going to connect that up like that. And then we have R5. I'm going to go over here. Again, that can be just a minimum with trace. Okay, that's pretty much it. We still have all the ground connections. This pin here this is ISET 2. I'm just going to connect that right into the power pad, which will be grounded. And I can do the same with the VSS pin. Then later I'll do a copper fill, and that will just come in. It will fill in all this area here and grab all of these grounds together.